This is part 2 of a 3-part video. In the previous video, we used DNS to predict the drag of a 3-dimensional sinusoidal surface. Another method which could be used to predict the drag of a surface is by using empirical models. These empirical models uses the topological features of a rough surface and relate it to the drag penalty. There have been various roughness function models which have been proposed in the open literature, and some of them can be found in Fleck and Schultz's 2010 paper. In this video, I would like to focus on two particular roughness parameters due to some discrepancies in the literature. The two roughness parameters of interest are the roughness average height, Ka, and the effective slope, Es. The roughness average height is defined as the mean of the absolute roughness fluctuations. Here is a two-dimensional sketch of a sinusoidal surface with large Ka, and here is a surface with a small Ka. However, Ka does not contain any information about the wavelength of the roughness elements, and therefore it is possible to have a surface with the same Ka but looks very different. Here is a plot of the roughness function against Ka+, and this plot is obtained from Acharya et al. In 1986. You can see from this plot that there are some rough surfaces which scales very well with Ka+, but there are some which don't. This leads me to the next roughness parameter of interest, which is the effective slope, Es. Es was first introduced by Napoli, and it's defined as the mean of the absolute streamwise gradient. It is also found that Es is 2 times of solidity. A surface with low Es would appear to be a wavy or undulating surface. On the other hand, a surface with high Es would appear spiky. However, Es does not contain any information about the height of the roughness elements, and therefore, it is possible to have a surface with the same Es but has a very different physical size. Here is a plot of the roughness function against Es, and there have been literatures which have suggested that the roughness function depends solely on Es. We do not agree with this, as the roughness function also has to scale with some measure of the roughness height, in which here we have selected it to be the roughness average height, Ka. To investigate the effects of Ka and Es in a systematic manner, 2 range of simulations were conducted. The first range of simulations conducted is where we geometrically increase the size of the roughness elements while maintaining a fixed h over lambda ratio. Here, we want to investigate the effects of increasing Ka plus while maintaining a fixed Es. The results for these simulations were presented in part 1 of the video. The second range of simulations conducted is where we decrease the wavelength of the roughness elements while maintaining a fixed h plus. Here, we want to investigate the effects of increasing Es while maintaining a fixed Ka plus value. The table here shows the cases simulated at Arita 180, where we have maintained a roughness height of h plus equals to 10 and alter the wavelength of the roughness elements. These cases are known as case S2. And here are the cases simulated at Arita 540, where the roughness height is held constant at h plus equals to 60. Now, we would like to look at the mean velocity profiles for these cases. In the inset plot, we have the roughness function plotted against Es. Looking at the mean velocity profiles for the cases simulated at Arita 180, you can see that there is an increase in the roughness function with decreasing roughness wavelength. We have repeated some of these cases at Arita 360, and we observe the same trend. This gives confidence that our low Reynolds number simulations at Arita 180 are able to provide reasonable estimates of delta U+. Here are the cases simulated at Arita 540, and immediately you can see that the roughness function when h plus equals to 60 is much larger than when h plus is equals to 10, as one would expect. Initially, we observe an increase in the roughness function with decreasing roughness wavelength. However, further decreasing the wavelength of the roughness elements does not result in substantial change in the roughness function. Considering the limits of Es, when Es approaches 0, delta U plus approaches 0 as the rough wall becomes a smooth wall. When Es approaches infinity, delta U plus also approaches 0 due to the sheltering effect of the densely and closely packed roughness elements. This is something which is known and has been published by Jimenez in his 2004 review paper on rough walls. Now, I would like to plot the roughness function against ES, and this is a plot which I showed you earlier on. Overlaying our data, you can see it does not follow the curve proposed by Napoli. In fact, if you overlay it with other numerical and experimental data, there is quite a bit of scatter in the plot. In particular, I would like to focus on these three vertical regions which contribute to the scatter. These cases are surfaces with constant ES but with varying values of Ka+, and this clearly indicates that Ka+ is an important roughness parameter. Now, plotting the roughness function against Ka and adding Achaya's data and changing the linear x-axis to a log axis, we observe that there are certain surfaces which scales very well with Ka+, and there are some surfaces which don't. It is found that these surfaces are surfaces with very low ES and appears to be wavy and undulating. These surfaces do not behave like a typical roughness. Therefore, we have shown that ES is also an important roughness parameter. Now, we can then plot the roughness function against both ES and Ka+ on a three-dimensional plot. It appears that these data lies on a linear log-log surface fit with constants alpha, beta, and gamma. I can then plot the roughness function, which we have obtained from numerical simulations or from experimental works, and plot it against our roughness function model, which is based on ES and Ka+ of a surface. This diagonal line here is where the roughness function model is approximately equal to the roughness function. If the data lies along this diagonal line, it means that our roughness function model is able to accurately predict the drag of a rough surface. If the data lies above this diagonal line, it means that our roughness function model overestimates delta U+, and vice versa. Plotting our data, it appears to follow quite closely to this diagonal line. We can also plot other experimental and numerical works, and here I have shaded the region of ±2 of the roughness function model. There is still quite a bit of scatter in the data. However, you can see that the collapse is much better than when just using Ka+ or ES. The proposed roughness function model also appears to be able to reasonably predict the drag of a surface in the transitionally rough regime. It is important to note that this roughness function model is simplistic and does not have the right asymptotes when ES approaches infinity, and also when ES and Ka+ approaches 0 due to the log terms. Also, there are other roughness parameters which should be included in this model to take into account the alignment or sheltering of the roughness elements. The work which I have presented here is published in the following paper. Thank you.